I love robots, and this is part one of making a robot arm, and it's going to be a very special robot arm because it's going to be force-driven. So in a previous episode I made this force-driven gripper which is going to be on the arm, but actually not this one because we need to do a redesign for various reasons, and check that video out. But basically what we've got is a spring in between the servo and the finger itself. So as we apply more force, of course that spring stretches more. We measure the finger position with a flex stroke bend sensor, and we know the servo position, and that means we can work out how much force we're applying. We then turn that round the other way, so instead of setting the position and measuring the force, we actually drive the force, and that makes the joint compliant. So we set the amount of force, and obviously if more tension is on those springs, it thinks there's more force, so that means we can back drive the joints and actually move them actively backwards, and the servos respond unless we turn the force up, and then they don't. So that's quite useful. It means we can measure how much force that's actually being applied to something, or we can set how much force we apply. So we need a bit of a redesign on that hand, as I say, but essentially this arm is going to follow those principles. Just a quick ad for my Patreon campaign. You can support me through Patreon and you can get access to the videos early, a live stream with me, and other sneak peeks and pictures. And if you don't like Patreon, I've got YouTube channel membership, so just click on that join button below. You can also get my merchandise in my Teespring store, the link is in the description. I've got Open Dog t-shirts, mugs, and lots of other things like that. And don't forget to of course check out the rest of my channel for all the other robotics builds, including Open Dog, the open source quadrupedal robot. So in order that gravity doesn't have too much of an effect on our force controlled arm, if we can imagine it's sort of one of these traditional looking robots that rotates in the middle, and it's got a joint that goes like that and one that goes like that, and then it can reach around for things. Obviously lifting up is going to require more force than putting the arm down, so that's going to complicate things. So what we're actually going to do is build a SCARA arm which kind of goes more like this. So all of the joints are vertical, all of those axes. It's got a shoulder and an elbow, and then a gripper that goes up and down on a linear slider. So my initial plan is to make a steel stand with a welded base, which is going to be 50mm box section steel, some 3D printed clamps that go round it that tighten up there to just hold it on with friction, a top and bottom plate which is CNC aluminium, and then have a shoulder hub we're going to build here, which is going to basically make the main compliance section. But I'm not quite sure if that is going to be the shoulder, or if it's just going to be the elbow, or if it's going to be both, or how it's going to work. So first of all, I'm going to try and make this force controlled hub. So the plan for the main hub is that we've got this driven hub which is going to have a belt drive on it from a motor which will be fitted on there, probably a T5 belt, and essentially that whole thing rotates on bearing blocks which are attached to something. It was just shown on the plates, top and bottom. So those have got big bearings in, there's a shaft that goes all the way through. And then the hub is made up of two main sections. So we've got a top and a bottom which are attached together with 2020 extrusion, and two shrouds which make that one piece, and then the internal part, and that rotates separately. And that basically means that the internal can rotate separately from the driven part, and we can work out the force. But in order to work out the force of the inner part against the outer part, we need some sort of spring that springs it back in the middle. So we've got these fingers here which basically are sprung together, and those are attached to this inner part. So that means they're locked together against this stopper, basically the big cross section in here, and also against the 2020 on the outer part, so that should keep everything central. But as the inner part turns against the outer part, then this means that either diagonal fingers this way will move, or diagonal fingers this way will move, and they'll start to pull outwards as this 2020 moves around. And that means we can measure the inner position against the outer position, and then we can work out what force is being applied. So I've already partly assembled this. This is our top and bottom, so these have got bearings in. So there's a tube that runs all the way through, and those will of course run on the bearing blocks, which are top and bottom on whatever it's mounted on. So basically this whole thing runs on bearings. And then we've got the internal part, which is this, which I've already put these little flaps on, and I've got another 4 to put on the bottom, and that should fit like so. So what will eventually happen is these flaps will be sprung together, and there's going to be more studding running in those that runs all the way down, so we can spring them together in the gap in the middle we've got there. And then basically that will hold this, so we'll hold the inner against the outer until we rotate it. And then of course 2 of these will spring away, but they'll want to spring back. And if we rotate it the other way, the other 2 will spring out, and those will want to spring back. So it's the same spring on each side that's holding those together, so we get the same tension, but the inner can rotate separately from the outer. And the inner is actually fixed to this shaft, so we've got the place here for 2 grub screws, so we can actually make sure this shaft rotates. And this of course sticks out of the bearing in the very top, so we can measure the position of the inner. And the outer is going to be driven by a belt drive or something that's sat on the bottom. Haven't decided whether it's a belt or a gear and a motor. We'll know the motor position, and then we can compare the 2 and work out the force, just like we did with the gripper. So now the springs go between those things, and they go through that gap on either side to spring those together, and that locks everything. So I've just installed some temporary springs either side there, just so those spring back. I've got some more on order. I think we're going to need more than 1 spring each side, which is why I've got so much space here. So we could put 2 or 3 or 5 or something in there. So I've fitted all that together, and of course this whole thing will rotate, driven by a motor. So that will move the main part of the arm around, but of course the internal turns separately from the outside, pushing those springs, and that's where we can work out the force that's been applied, because of course as we push it more, the spring stretches more and it gets tighter and tighter. And so that will allow us to calculate the force by looking at the difference between the outer and the inner. So this is going to make either the shoulder or the elbow joint, and then of course we need another joint for the other joint of the arm. So I think what I'm actually going to do is back to back 2 of these. So we've got this 2020 extrusion plugged in. If I just get 2 of these and stick them together, then we'll have the 2 joints. The only thing is the motors need to be fixed on what will be the stationary part. So on the shoulder that'll be the main support, but then on the elbow it'll effectively have the motor on the forearm, which will add a bit of mass. But I think it's a pretty rigid assembly. It doesn't have to be much longer than that really, so I think that's probably the best way to do it. Yes, it's another whole set of parts and needs assembling to make the other joint. So now I've got 2 of those back to back with this 2020 that's screwed in there, and so obviously we can measure the load on each one there. We can measure the amount of force, because we've got these 2 hubs that turn independently. So one is going to be attached to the forearm, and the other one is going to be attached to the stand. Yes, I've made a giant metal stand. It's got 4 adjustable feet, so I can get it perfectly upright in case my welds aren't square, but I'm pretty happy with that, and some of my welds are looking pretty good now. Yeah, it's pretty big. It's about 5 feet tall. I think this is a 1.5 meter thing, and it's off the ground on its feet, and that means we can put a table over here, and then the arm can go on here. And basically that means that it can fish over the table to get things and so on, and it's on a sturdy base on the floor. Now we might need some extra supports, another cross brace perhaps down here, but we'll see how it goes. Obviously that will have to be under the table height. So I've now got these which are split in 2 halves, and they've got some bolts that go through there, and that should clamp onto that upright. So I've hardly done those bolts up, but those are actually quite strong, so that's pretty good. And then of course this will fit in here, so this will be the shoulder, and that will allow quite a bit of rotation there. And then of course we need to put the forearm on, sticking off this piece here. So what I showed in the original CAD were CNC plates, top and bottom, and I think that's still going to be true, but the configuration of those is going to be dependent quite a lot on how this fits on, which could just be a plate, obviously with the bearings top and bottom, but we've also got to get the motor in, so that needs to be mounted somewhere. So in terms of motor choice, we're either going to use these motors that I used in OpenDog, which are the Turning G SK3 range, the 6374 149 kV motor, but it's brushless, so we're probably going to need the O drive and an encoder on each one. Of course this is a dual motor driver, and that's good because we need 2 motors basically for those 2 axes. Obviously the wrist actuator and all that stuff will sort out separately. So that's one choice. This is a 2 kilowatt motor. It does go extremely fast. We're going to need some intermediate gearing if we do that, which might introduce more backlash. The other alternative is this quite big DC motor with an integrated gear head, so we can just put a gear on there and run it straight on our main pieces of the assembly there. So this one's from Gimson Robotics. They do quite a lot of different ratios and so on. This is a 71.2 to 1 ratio. Looks like a planetary gearbox. Unfortunately, there's nowhere to mount an encoder. There's a little stump on the bottom, and I'm going to actually put an encoder on there, or try and mount an encoder on the back and see how accurately we can control that, because otherwise it's going to be very difficult. So this is the place that I've left to put the pulley or the gear or whatever we have that goes to the motor. So we'll have to mount the motor sort of like this or like this, and then basically have a pulley or a gear on there. It could be a pulley and a belt. Obviously there'll be some stretch in the belt, or a gear or whatever that goes on to this. So we could obviously put a piece on here that's much fatter, and I've just left this here so there's lots of space to glue it on. We can make it as big or as small as we want, and we can attach it to whichever motor, but obviously mounting this motor is going to be the tricky thing. So I'm pretty happy with how that's worked out so far, and my lovely metal stand. Next time we're going to be trying to do encoder control of this motor and looking at the CNC mounts to put this on the stand, and talking about the forearm. Then of course after that we need to go and put the axis that goes up and down, that linear axis for the gripper, and eventually build a new gripper as well, which is also going to be force controlled. So don't forget to subscribe for more updates on this project and all the other projects. Alright, that's all for now.